This is problem 224 on page 35. Determine the x and y components of each of the forces shown. What we'll do is do what they've said, and then we will figure out the resultant, or the sum, if you will, of all those forces and their effect on the body. So we've got some type of a branch hanging down from the ceiling, looks like. Y-axis here, horizontal x-axis running through the center point. And the center point is where we have three forces applied. Let's see, something like this. 150 pounds at an angle of 40 degrees, horizontal. 120 pounds at an angle of 45 degrees from the next force. And then at 30 degrees, we've got a force of 80 pounds. We're supposed to find the components of each of these forces. That shouldn't be too bad. But let's just talk about this before we do it. Well, let's start with the 80-pound force. It's the easy one. The 80-pound force, does it have a positive or negative x component? Positive. What about y component?
Negative.
Negative. How about all the forces y component? All negative, aren't they?
Yeah.
How about the horizontal component of the 120-pound force? Where's positive or negative x?
Positive.
Positive. More than or less than the other one? What do you think?
It's
Not a fair question, is it? Because this one's bigger than that one. I haven't drawn them to scale. It's possible that this one's really, really short and doesn't go out as far on the horizontal axis as this 120-pound force. But given that extreme angle, the fact that these are too close, your engineer brain ought to say, you know what, that one probably doesn't have as much horizontal component as that one has. Obviously, it has a lot more vertical component. It has to have more vertical component. Not only is it a bigger force, it's also at a steeper angle. So certainly this is a larger force in the y direction than this one is. X, not so sure, but pretty sure this one's still going to have a larger x component. What about this one? What would you say about its components? Positive or negative?
Negative.
Both negative, right? Because both in the negative coordinate directions. Okay. So we expect to get negative, negative. If we're going x, y, then positive, negative, and then positive, negative again in terms of the coordinates. Go.
Is that 120 pounds force 45 degrees from the horizontal, or 45 degrees
from
from,
the other-
30 degrees?
From 30 degrees, according to the image.
Okay.
Yeah. So that would be what? A total of 75 degrees? That'll make our lives easier to have that number. Okay. So calculating the horizontal and vertical components of these things would be pretty easy. All we have to do is say that the x component is 120 pounds multiplied by, well, do we need sine or cosine? What do you think? Let me show you a trick when you're not sure. Extract the angled line, draw lines, it doesn't matter which side, draw lines parallel to the coordinates. Put them on either side that you like. It doesn't make any difference, you'll get the same thing. Put the angle where it belongs. In other words, this angle is with respect to horizontal line. The angle is right here, in other words. 75 degrees is right there. Where else is there 75 degrees? Right there. Remember interior opposite angles, I think it's called?
That's right.
Okay, being equal? Okay. Because we know these two lines are parallel. Now that you've got that, now that you can see the triangle, now answer the question. We wanted a horizontal component. That's this. It's touching the angle, therefore it must be the cosine side. Because if it touches the angle, it's cosine. Okay? So we just need to multiply by cosine of 75 degrees. So go ahead and do that if you would. The y component then will be just 120 pounds multiplied by the sine of 75 degrees, won't it? Warning, a Sisk trap ahead. I try to push you into holes. Don't let me do it. These are easy mistakes to make. This one will come out okay. Anybody got a number for 120 times cos 75? $31.05, thank you.
058.
06. So if you multiply 120 pounds by sine of 75 degrees, will you get the magnitude of the vertical component of the 120 pound force? It's easier than you think. Yes, there's a problem here, but it's easy. Go ahead and do it. It won't be useless. Take 120 pounds, multiply by sine of 75. What number do you get?
115.91 pounds force.
Why can't I just say that the vertical component of that 120 pound force is 115.9? Because it's negative. All right. We just said that the y component was a negative thing. Okay, so be careful. When you make a triangle like this and you look at the angle, your brain is already thinking or already going towards, oh, we're in the first quadrant. There's the sine side, there's the cosine side. No, this is the negative sine side because we're in a different quadrant. You see? So just be a little bit careful about that. So now we have the components of the 120 pound force. Let's do the same thing for the 80 pound force because really it's almost the same thing, isn't it? It's just that the angle, I don't know why I erased the angles, I should have erased the numbers. The angle is now 30 degrees, and I know this doesn't look right, but why bother drawing another rectangle? It would just be landscape instead of portrait, wouldn't it? Okay? But 30 degrees is fine. We're going to do the same thing. The x component is simply going to be 80 pounds multiplied by the cosine of 30 degrees. And of course the y component would be 80 pounds, well, negative 80 pounds, times the sine of 30 degrees. If you really wanted to, you can measure the angle from the horizontal axis all the way around. So that would be, what, 330 degrees? And then if you took sine and cosine of 330 degrees, the sine, the SIGN, would come out automatically. Okay. Well, what do we get at 80 times cos 30 degrees? What's that? I'll do this one for you. The sine of 30 is a half, if I remember right.
80 pounds times the cosine of 30 is 69 point, wait, what? Yes.
69 point what?
In significant figures, wouldn't it be,
Oh, just give me a couple of them, we'll figure it
Okay.
out later.
0.28?
Okay. You'll see why I've kept a couple of significant figures here in a second. To me, we're still in the middle of the problem. We're not done yet. Okay. How about this 150 pound force? What do you know about the horizontal vertical components? You know they're both negative, don't you? So now, can you tell me whether the x is going to have cosine or sine of 40 degrees in it? What do you think? If it's difficult, draw yourself a little triangle and a square. Just extract this line, pull it over to the side, finish it off with some horizontal vertical lines, and look at it. Don't try to do math in your head. It doesn't work very well. It's easier to do it on paper. How many people think I need to multiply 150 by, well, negative 150 times cosine of 40 degrees in order to get the x component? How many people think I need to use sine instead? Good. I won't belabor the point. You're all correct. Cosine of 40 degrees, sine of 40 degrees. Is it because cosine always goes with horizontal and sine always goes with vertical? After all, that's what's happened so far. No, it's not. The only reason this has worked is because we're measuring relative to a horizontal axis. That's the only reason that cosine has gone with x and sine has gone with y. If we measured relative to a vertical line, they'd be flip-flopped, right? To get the vertical component, then we use cosine. To get the horizontal component, we use sine. Okay? So 150 times cosine of 40 degrees is what? And 150 times sine of 40 is what, please?
For negative 150 times cosine of 40, it's negative 114.91.
Okay?
And sine is 96.42.
Or negative 96, or yeah, negative 9.
Sure. Perfect, thank you. So now we have the horizontal and vertical components of all of these forces. Could we figure out what the total force is on this bracket? I think we could. Why would we care? Well, because think about it. Whatever bolts we put in this thing, it better hold it to the ceiling or whatever. Maybe it's a piece of angle iron, or maybe it's an I-beam or something, whatever. However much these forces come up to is gonna have to be supported there at the top. Yeah, it's gonna be a force at two different places, don't worry about that right now, we just need the total externally applied load on the bracket so we can figure out how much the reactions have to be. So how do we calculate, since it looks like we'll probably end up with something like this, I'll just draw it there, sorry it's going into my math, but this resultant, how do we calculate its magnitude? What would you do?
Add each of the components for each of the
X and Y.
planes.
Exactly. So this reaction, or not reaction, excuse me, this resultant in the horizontal direction would be, well, the horizontal component here is 69.28. The horizontal component from the 120 pound force right here, so it's 31.06. And notice that one did come out smaller, just as we said it, we suspected it would. And then the 150 pound force gives us minus 114.91. And these, of course, are all pounds force. And then the resultant in the y direction would be, well, let's see, negative 40 minus 115.91 minus, let's see, 96.42, and these are all pounds force. Okay? So take your calculators, please, and tell me the results of all this addition.
The X is negative 14.57.
14.57. Okay. How about the y component, somebody?
Negative 252.33.
So there are the reactions in the horizontal and vertical directions. So the resultant force, what's wrong with what I drew here?
Go the wrong side.
Wrong direction, isn't it? It ought to be something more like this. There's where it ends up. How do I know that? Because the horizontal component was negative. Just barely, but it's negative. So that means that in terminology of unit vectors, the vector r is equal to rxi plus ryj, or in other words, it is negative 14.57i minus 252.33j, and these are both, I think usually we're supposed to put square brackets around vectors, aren't we? These are pounds force. Could we calculate the magnitude of that vector? Sure. Plug these two into Pythagorean's theorem and we'd have it, right? So 14.57 squared plus 252.33 squared and the square root. So let's do that if you would. Tell me what we get. You can plug in the negative sign if you like on each, but of course once you square the numbers it won't make a bit of difference. Obviously we'll get a positive magnitude out of here. How's it possible to get a positive magnitude when we've got a negative vector?
Because magnitude isn't
It's not directional, right? So it's not a negative thing, it's just how long it is. All right? I guess I should write that these are pounds force.
um 252.75.
If we look at this, does that make sense? You might be thinking, well, if I were to add about 15 to about 250, I would expect to get about 265. But I get something pretty doggone close to the original number. Why? Because there's not a whole lot of angle. In other words, the length of the vector is about equal to this component of it, right? Because, and that's the vertical component, that's right here. Because this just doesn't add much to the overall tip to tail length, right? So it's not really a surprise that comes out just slightly larger than the vertical component. What else could we ask? Well, we could ask about the angle. Let's call the angle phi, just for fun. Why? Well, because we use alpha, beta, gamma, phi, and of course theta most often for angles, okay? So since we haven't really used phi left, I guess it's feeling left out, or I think it is, so we'll join it and have it come to the party, okay? So we're going to take an inverse tangent, of course, but what are we going to take an inverse tangent of? Well, it depends on which angle we want. If we want this angle, what would be the y component, or what would go in the numerator, and what would go in the denominator? If we say we want this angle, will this length go in the numerator, or will this length? In other words,
Opposite of
it'd be opposite, so it'd have to be Rx over Ry, wouldn't it? On the other hand, so this is the angle phi. If instead what we wanted was this angle, and let's call it, I don't know, let's get rid of all this, we don't need all that anymore. Let's call this, I don't know, beta. Why? Well, because we usually use alpha, beta, gamma, or feeling like rebels today, so we use beta, skip alpha, right? If we want beta, we're going to have to take the inverse tangent of something. What will we take the inverse tangent of? Give me the numerator. No. What's that?
Or y over Rx.
Ry over Rx, because notice beta, right there, isn't it? So we need this vertical component over the horizontal component, so Ry over Rx. Calculate whichever one you like, I don't care, take your pick. In fact, let's have this side of the room give us phi, the other side you guys give us beta, okay? See what we get. But be careful, are you going to plug in two negative numbers? You can. If you have a calculator that uses an atan, an inverse tangent, or arctangent function that's usually referred to as atan2, and you put in a separate x and a y number, and both are negative, what it does, atan2 actually gives you an angle in all four quadrants, so relative to the first, horizontal axis. If you simply use an inverse tangent function, which is what most calculators have, then you'll simply put in a ratio, and the negative signs won't matter because they will cancel. Okay. If you use an atan2 function, you'll get an angle more than 180 degrees. There are reasons for using that, but none here.
Yeah.
How much?
86.69.
86.69?
Yes, sir.
Thank you. Does that seem reasonable? Sure. This vector doesn't have much vertical components, so we expect to get something close to 90 degrees, don't we? Yep. How about phi? What did phi come out to?
3.30.
I just thought of something. Why don't we call angles phi instead of just phi? That'd make it more interesting. Sound like a dog's name. Okay, so there it is. That's it. We know the magnitude of the vector. We know exactly what its direction is, measured relative to vertical or horizontal. Take your pick. And that's it. Of course, they didn't ask for this, but we gave it to them anyway. Any questions?